Okay, today we still study Taylor's theorem. From the beginning to the end of this course, we often use Taylor's theorem. Taylor's theorem has several forms. First, take a review about one notation. This notation. C means continuous. This notation means the set of all functions defined on the open interval. AB. And this function has derivatives up to order n+1, where function f, first derivative, second derivative, and derivative n+1 times, they exist. And all are continuous on the open interval A to B. Now, let me present Taylor's theorem in several forms. The first form, it is called Taylor's theorem with Lagrange remainder. Remainder here means the error term. Suppose function f is in this set. Then for any 2 points, C and X from the open interval AB, we have the following formula. F of X is equal to F of C. C is a constant, X is a variable, plus 1/1 factorial F derivative as C times X minus C plus 1/2 factorial second derivative as C X plus C square, and so on. This term is the n+1 term. C, X plus C is n. This equation, left-hand side is a general function. The right-hand side is a polynomial. They don't equal. So we need to add an error term to make this equation true. So the error term plus error term depends on n, also depends on X, also depends on C actually. Yeah. Where the error term, this error term is called Lagrange remainder. The error term is very similar to the last term here, very similar. 1 over n plus 1 factorial. Here is n factorial. Here is n plus 1 factorial. Here, derivative n times. Here, in the error term, derivative n plus 1 times. Evaluate at some point sign. What sign is? We don't know. Usually, we don't know what sign is. X minus c n plus 1, where psi is between, we only know psi is between, not including, is between c and x. This formula is called Taylor's theorem with Lagrange remainder. One special case about this formula. Let me give a name to this formula. Formula 1. One special case. Special case. C is 0. Then formula 1 becomes, we often use this special case. F of x is f of, now c is 0, so f of 0 plus 1 over 1 factorial derivative at c, now c is 0, times x minus c, so x, c is 0, plus 1 over 2 factorial, f second derivative at c as 0, x minus c squared, so x squared, and so on. This term is the n plus 1 term. Derivative n times evaluate at c as 0, x to the n plus error term, where the error term is n plus 1 factorial derivative n plus 1 times evaluate a sign times x minus c. So x to the n plus 1. Okay, now sign is between 0 and x. We often use this special case formula. This is Taylor's formula with Lagrange remainder. Okay, this polynomial, we usually call it Taylor's series. Taylor's series. Now, this is the first form about Taylor's theorem, Lagrange remainder. A. Now B. B. Oh, B is also a special case. No, this is a case, special case 1. A special case 2. Special case 2. In this Taylor's formula, C and X is in AB. Now, let me, okay, then C is X, and X is X plus h in formula 1. Yeah, in this formula 1, c is x. This x is x plus h. Of course, suppose x and x plus h are both in the interval AB. Then formula 1 becomes this, okay? F of x plus h is special case we often use. Is equal to f of x plus 1 factorial f derivative x times x minus c. Now x plus h minus x. So this is a h plus 1 over 2 factorial f second derivative at x minus c square, x plus h minus x, then square. So h square, and so on. And factorial f n derivative, okay, times h to the n, then plus the error term. Now this error term depends on n, depends on x, also depends on h. So according to the book, write the error term E and H, where E and H is 1 over n plus 1 factorial derivative n plus 1 times evaluate at some point sine, then times x minus c. Now x minus c is h. Now h n plus 1. Okay, where sine is between x and x plus h. Special cases. This is a Lagrange remainder. Second form of Taylor's theorem, B. Taylor's theorem with integral remainder. Again, suppose function f is in this set. Then for any 2 points C and X from the open interval AB, we have f of x is equal to the polynomial is the same. F as c, 1 over 1 factorial f derivative as c, then x minus c, 1 over 2 factorial f second derivative as c, x minus c squared, plus 1 over n factorial f n c x minus c n n, then plus error term Now the other term is in integral. En of x is 1 over n factorial. Pay attention. Here, it is not n plus 1 factorial times integral from c to x f n plus 1 derivative t times x minus t to the n dt. In this integral, x and c are considered constants. T is a variable. So after we evaluate this integral, then we get a function only depends on x. C is a constant, x is a variable. But in this integral, x is considered to be a constant. After this, after we compute this integral, then we get a function of x. This is a Taylor's theorem with integral remainder. C, the next form. C. Taylor's theorem in two variables. Here, it means that the function f depends on two independent variables, x and y. Then this theorem is about a function of two variables. Again, a rotation. Okay, rotation. Let omega below is AB open interval, CD open interval. AB open interval by CD open interval. That means that is rectangle. Let me draw an XY plane. XY plane. Suppose A is here, B is here, C is here, D is here. Open. Open doesn't include the endpoints. Open. Then this interval by this interval means this rectangle. This rectangle doesn't include the boundary. This rectangle. Omega. This is omega. 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 And this is rotation one. And second rotation. C n plus 1 omega. This is the set of all functions. Those functions depends on x and y. Okay. All functions f, where f and now this time partial derivative n plus 1 times. There were many partial derivatives. Say derivative with respect to x, with respect to y. This is an order 1 partial derivative, and order 2 partial derivative. Take derivative with respect to x twice. Take derivative with respect to x first, then to y. Take derivative with respect to y, then to x. Take derivative with respect to y, then to y. This is a order 2 partial derivative, and so on, until order n plus 1. All these partial derivatives are continuous. On this rectangle. So this notation means the set of all such functions. Okay, now with this notation, let me present Taylor's theorem in 2 variables. Taylor's theorem in 2 variables. And then function f is in this set omega. In this set omega. Okay. Okay. Now if xy and x plus h, y plus k in the rectangle, inside the rectangle, yeah, here. I say this point x plus y, xy, and this point x plus h, y plus k. These 2 points are in omega. Then we have the following formula. F x plus h, y plus h. We can expand it in polynomials. This time because okay, see here. This is a f xy first term, second term 1/1 h partial x plus k partial y f of xy, second term. The third term, factorial x h partial x plus k partial y square. And plus the third term, 1 free factorial h partial x k partial y to the third f of x f xy, and so on. The n plus 1 term is a 1/n factorial h partial x plus k partial y and f x1. Then plus error term. Plus error term. Error, of course, depends on n, depends on x, depends on y, also depends on h and k. Okay. Then where the error term. Okay. The error term is similar to this term, very similar. The error term is n plus 1 factorial. Then here is h partial x, k partial y, n plus 1. The power is n plus 1. Then x1. Compute this derivative, then plug in this point. After you compute this derivative, plug in this point. X plus data. What is data? I don't know. It depends on x, y, h, and k, and n. But what I know about data is it is a number between 0 and 1. Data, k. Okay, where data, some point between 0 and 1. Between 0 and 1. Between 0 and 1. Compute this derivative, then plug in the point. So n plus 1 factorial h partial x, k partial y, power n plus 1. Okay, plug in the point. X data h y plus data k. Yeah. This is a Taylor's theorem in two variables. Let me explain. Let me pick this term to explain. Okay. In details. Okay. Explanation. Let me pick h partial x plus k partial y square. This is a derivative. What this derivative means? It means h partial x, k partial y times h partial x plus k partial y, f of x, y. Now expand this product by distribution. Then we get h first term times first term h square, partial times partial square, partial x square plus first term times second term h times k, partial times partial square times partial x times partial y. Second term times first term k times h, partial times partial square over partial y times partial x, then plus second term times second term k square partial y square, then f xy. Now distribute f of xy to all the terms. Then we get h squared partial square partial x squared f xy plus h k partial square partial x partial y f k h partial square partial y partial x f xy plus k square partial square partial y square f xy. Okay. Yeah, the first term derivative, partial derivative with respect to x twice. So the notation is f x x. Second term. This derivative means take derivative with respect to y first, then derivative with respect to x. So f second term, the derivative, take derivative with respect to y first, then to x, plus the third term. This derivative is take derivative with respect to x first, then y. So it is a h k f x first, then y, then plus derivative in the last term k square f y y. Because we assume that function f is in Cn plus 1. We assume the function is from this set. Therefore, f y x f x y both continuous on this rectangle omega. When these two derivatives are continuous, theoretically, we can prove that f y x is equal to f x y. Say, for example, psi xy. Take derivative with respect to x first, then to y. The result is the same with derivative with respect to y first, then x. Have a check. So this guy and this guy equal h times k, k times h equal. Therefore, this sum is equal to h squared f x x plus 2 h k f x y plus k squared f y y. Yeah, this is this term about what this term means. This term means this, means this, is this. This is a Taylor's theorem in two variables. Very similar. Taylor's theorem in m variables. Say, for example. Very similar. This is a C or D. A D. Taylor's field. In I say in K variables. In K variables. So the function depends on K independent variables. The formula is let x1, x2, xk, and sk plus 1 x2 plus x2, xk plus hk. These 2 points is in omega. Now omega is a rectangle in k-dimensional space. Okay. Then the formula is f x1 plus h1, x2, x2, xk, hk. We can expand this into f x1, x2, k plus second term 1/1 factorial h1 partial derivative x1 plus h2 partial derivative with respect to x2 and hk partial derivative, then f x1, x2. This is a first term, second term. The third term, very similar to factorial. And then let me, okay, here, okay, in details. Partial, a 2, right? How to find this square? Expand it, okay, expand it. Expansion. Third term, and so on. N plus 1 term, very similar. H1 partial x1, H2 partial x2, K partial sk. Now the power is n. F x1, x2, xk. Very similar. And then add an error term. Now error term depends on n, depends on all the x and all the h. Where the error term very similar. The error term is n plus 1. Okay, then here, yeah, here, n plus 1. This part, this sum goes here. Take derivative on the function. After we get this derivative, plug in this point. x1 plus data h1, x2 plus data h2, very similar, and xk plus data HK. What is data? We don't know. We only know data between 0 and 1. Very similar. This is a Taylor's theorem in K variables. Now, one example. Let me show you one example. One example. Example. Consider this function. The function is cosine x, y. Okay, consider this function. Okay, now expand this function by Taylor theorem. Expand the function 2 terms. Okay, 2 terms. Okay, yeah, use this formula. F x plus h, y plus h. First term is f x y. Second term, h partial x, k partial y, f x y, and then also write the error term in detail. Now the error term n should be 1. 1. Okay. HK. Okay. HK. Okay. Where the error term by formula, it is n is 1. So n plus 1, so 2 factorial. H partial derivative, k partial derivative, 2, the power is 2, then xy, then plug in this point, data h y plus data k. Yeah. So we need to compare first and second order partial derivatives on the function. Okay. Say partial x cosine xy. Yeah. To compute this partial derivative, consider y as a constant. So by chain rule, take derivative with respect to x, then negative sine xy, then derivative on x times y with respect to x, so times y, so negative y sine xy times xy. Okay, now compare partial derivative with respect to y. Cosine xy. Now this time x is a constant, so again negative derivative with respect to y by chain rule, negative sine xy times x, so negative x sine xy. As we have seen that this is equal to where? Let me see, go back to my notes. This is h square. When I expand the square, f xx plus 2 hk f xy plus k square f y. Okay, now we need to compare f x y. That means that take derivative with respect to x first, then we get this. So this is a negative y sine xy. Yeah, this is derivative with respect to x. Now take this derivative with respect to y. Now this time, x is a constant, y is a variable. So to compute this derivative, chain rule, by chain rule, take derivative on y by chain rule. Then we get negative by chain rule sine xy minus xy cosine xy. Am I right? Derivative minus y cosine. Yeah, correct. By chain rule. And similarly, to compute derivative xx, very similar. And then compute derivative yy, very similar. Then we get h partial x plus k partial y square f xy. This derivative is equal to negative h square y square cosine x y plus 2 hk times xy cosine xy plus sine xy. Then minus k square x square cosine xy. Yeah, this second derivative is for the error term. After we compute this second derivative, plug in this point in xy, then we get the error term. And then plug in the error term here. Plug in cosine xy here, and first derivative here. Then we answer this question. This question is a write this function into two-term Taylor's series. This is all for today's class. Today is only about Taylor's theorem, section 1.1. In the next class, we will study section 1.2.